Welcome to this comprehensive video on sine sum to product identities. Today, we'll explore one of the most powerful tools in trigonometry. Sum to product identities are mathematical formulas that allow us to convert sums or differences of trigonometric functions into products of trigonometric functions. These identities are incredibly useful for three main purposes: simplifying complex trigonometric expressions, solving trigonometric equations more easily, and performing integration in calculus. In this video, we will learn the four main sum-to-product formulas, understand how they are derived, work through practical examples step by step, and apply these identities to solve real mathematical problems. By the end of this video, you'll have a solid understanding of sum-to-product identities and be able to apply them confidently in your mathematical work. Now we'll examine the two fundamental sine sum to product formulas that form the foundation of this mathematical technique. The first formula deals with the sum of two sine functions. When we have sine of A plus sine of B, we can transform this into a product form. This sum equals 2 times sine of A plus B over 2 multiplied by cosine of A minus B over 2. Notice how we've converted a sum of sine functions into a product involving both sine and cosine. This transformation is the key to simplifying many trigonometric expressions. Now let's examine the second formula, which handles the difference of two sine functions. The second formula transforms the difference of two sine functions. When we have sine of A minus sine of B, we get a different product form. This difference equals 2 times cosine of A plus B over 2 multiplied by sine of A minus B over 2. Notice the important difference. For subtraction, we get cosine times sine, whereas for addition, we had sine times cosine. The order in functions change based on whether we're adding or subtracting. Here are both formulas side by side. The top formula handles addition of sine functions, while the bottom handles subtraction. Both convert sums or differences into products. The left sides show the original sum or difference of sine functions that we want to simplify. These formulas are incredibly useful because they convert sums and differences into products. Products are often much easier to work with in calculus, especially for integration. They also help simplify complex trigonometric expressions and are essential tools for solving trigonometric equations. These two formulas form the foundation of sine sum to product identities. In the next section, we'll explore how these formulas are derived and understand the mathematical reasoning behind them. Now that we've seen the sine sum to product formulas, you might be wondering where these identities actually come from. Understanding their derivation not only helps us remember them better, but also reinforces their mathematical validity. The sine sum to product identities are derived from the product to sum identities. These fundamental relationships show us how to convert products of trigonometric functions into sums. We'll focus on the first identity to derive our sine sum formula. The key insight is to use clever substitution to transform this product form into a sum form. Here's the clever part. We make a substitution where u equals a plus b over 2 and v equals a minus b over 2. This might seem arbitrary now, but you'll see why this works perfectly. Now we solve for a and b in terms of u and v. When we add u plus v, the b terms cancel out, giving us a. When we subtract u minus v, the a terms cancel out, giving us b. So we have a equals u plus v and b equals u minus v. These relationships are crucial for our substitution. Now we substitute our expressions back into the original product to sum formula. We replace u with a plus b over 2 and v with a minus b over 2. On the right side, u plus v becomes a and u minus v becomes b. Finally, we multiply both sides by 2 and rearrange to get our sine sum to product identity. This shows that the sum of two sines equals 2 times the sine of the average times the cosine of the half difference. This step-by-step derivation shows us exactly why the sine sum to product identity works. It's not just a formula to memorize, but a logical consequence of the fundamental product to sum relationships. Understanding this derivation helps us see the deep mathematical connections between different trigonometric identities. The same substitution technique can be used to derive the other sum to product identities. Each follows the same logical pattern of clever substitution and algebraic manipulation. Now we'll work through our first example to see how the sine sum to product identity can simplify trigonometric expressions. This example will demonstrate the practical application of the formula we've learned. Our problem is to simplify the expression sine of 3x plus sine of x. We want to transform this sum into a simpler product form using our sum to product identity. We'll use the sine sum to product formula. This formula states that sine of a plus sine of b equals 2 times sine of a plus b over 2 times cosine of a minus b over 2. First, we need to identify our a and b values. Comparing our expression with the formula, we see that a equals 3x and b equals x. Step 1, we calculate a plus b over 2. This gives us 3x plus x over 2, which equals 4x over 2, which simplifies to 2x. Step 2, we calculate a minus b over 2. This gives us 3x minus x over 2, which equals 2x over 2, which simplifies to x. Step 3, we substitute our calculated values back into the sum to product formula. Substituting our calculated values, we get 2 sine of 2x times cosine of x. Therefore, our original expression sine of 3x plus sine of x simplifies to 2 sine of 2x cosine of x. Notice how we've transformed a sum of two sine functions into a product of sine and cosine functions. This product form is often much easier to work with in calculus and other advanced mathematical applications. Now we'll tackle a more challenging application, solving trigonometric equations using our sum to product identities. This is where these formulas really show their power in simplifying complex problems. Here's our equation. Sine of 5x minus sine of 3x equals 0. Our goal is to find all values of x that satisfy this equation. Step 1. We need to apply the sign difference formula. Recall that sine of a minus sine of b equals 2 cosine of a plus b over 2 times sine of a minus b over 2. Step 2. In our equation, we identify a as 5x and b as 3x. This will help us substitute into our formula correctly. Now let's substitute these values into our formula step by step. Step 3. We substitute a equals 5x and b equals 3x into our formula. This gives us 2 cosine of 5x plus 3x over 2 times sine of 5x minus 3x over 2. Step 4. Let's simplify the expressions inside the trigonometric functions. 5x plus 3x equals 8x, and 5x minus 3x equals 2x. Now we can simplify the fractions. 8x over 2 equals 4x, and 2x over 2 equals x. So our equation becomes 2 cosine of 4x times sine of x. Now we have our equation in a much simpler form. Let's set up the complete equation and solve it. Our equation is now 2 cosine of 4x times sine of x equals 0. Step 5. We apply the zero product property. If a product equals 0, then at least one of the factors must be 0. This gives us two cases to solve. Either cosine of 4x equals 0 or sine of x equals 0. Now let's solve each case separately to find all possible values of x. Case 1, cosine of 4x equals 0. Cosine equals 0 when the angle is an odd multiple of pi over 2. So 4x equals pi over 2 plus n pi, where n is any integer. Dividing both sides by 4, we get x equals pi over 8 plus n pi over 4. Case 2, sine of x equals 0. Sine equals 0 when the angle is a multiple of pi. So x equals m pi, where m is any integer. Our complete solution combines both cases. X equals pi over 8 plus n pi over 4, or x equals m pi, where n and m are any integers. This gives us all possible values of x that satisfy our original equation. Notice how the sum to product identity transformed a seemingly complex equation into a simple product that we could solve using basic trigonometric principles. This demonstrates the real power of these identities in problem solving. Sum to product identities have powerful applications in calculus, particularly when we need to integrate products of trigonometric functions. These identities can transform difficult integrals into much simpler ones. When we encounter integrals involving products of sine and cosine functions, they can be quite challenging to solve directly. However, sum to product identities provide us with a powerful tool to convert these products into sums, which are much easier to integrate. Let's work through our first example. We want to integrate the product of sine of 3x and cosine of x. This is exactly the type of integral where sum to product identities shine. Step 1. We apply the sum to product identity for sine A cosine B. This gives us 1/2 times the sum of sine of 3x plus sine of 3x minus x. Step 2. We simplify the arguments. 3x plus x equals 4x, and 3x minus x equals 2x. So we have 1/2 times sine of 4x plus sine of 2x. Step 3. Now we can integrate the sum. The integral of sine of 4x is negative 1/4 cosine of 4x, and the integral of sine of 2x is negative 1/2 cosine of 2x. Don't forget the constant of integration. For our second example, we'll integrate the product of two sine functions, sine of 5x times sine of 2x. This requires a different sum-to-product identity. For products of sines, we use the identity sinA sin B equals 1/2 times cosine of A minus B minus cosine of A plus B. Applying this identity, 5x minus 2x gives us 3x, and 5x plus 2x gives us 7x. So we have 1/2 times cosine of 3x minus cosine of 7x. Now we integrate. The integral of cosine of 3x is 1/3 sine of 3x, and the integral of cosine of 7x is 1/7 sine of 7x. This gives us our final answer. Our final example involves the product of two cosine functions. We'll integrate cosine of 4x times cosine of 2x using the appropriate sum-to-product identity. For products of cosines, we use cosine A cosine B equals 1/2 times cosine of A minus B plus cosine of A plus B. This gives us 1/2 times cosine of 2x plus cosine of 6x. Integrating the sum, the integral of cosine of 2x is 1/2 sine of 2x, and the integral of cosine of 6x is 1/6 sine of 6x. This completes our integration using sum-to-product identities. The key takeaway is that sum-to-product identities are incredibly powerful tools in calculus. They transform difficult integrals involving products of trigonometric functions into much simpler integrals involving sums, making integration straightforward and manageable. Sum-to-product formulas are powerful tools for verifying trigonometric identities. When we verify an identity, we prove that two expressions are mathematically equivalent by transforming one side to match the other. Our strategy is straightforward. We start with an identity that needs to be proven, then apply sum-to-product formulas to transform one side until it matches the other side exactly. For our first example, we need to verify this identity. We have sine of 5x plus sine of 3x equals 2 sine of 4x cosine of x. We'll use the sum-to-product formula for sine. Sine of A plus sine of B equals 2 sine of A plus B over 2 times cosine of A minus B over 2. Step 1, we identify A and B. In our expression, A equals 5x and B equals 3x. Step 2, we calculate the arguments. A plus b over 2 equals 5x plus 3x over 2, which simplifies to 8x over 2, giving us 4x. A minus b over 2 equals 5x minus 3x over 2, which simplifies to 2x over 2, giving us x. Step 3. Applying the formula gives us sine of 5x plus sine of 3x equals 2 sine of 4x cosine of x. This matches our right side exactly, so the identity is verified. For our second example, we have a more complex identity. We need to verify that sine of 7x minus sine of x equals 2 cosine of 4x sine of 3x. This time we use the sign difference formula. Sine of A minus sine of B equals 2 cosine of A plus B over 2 times sine of A minus B over 2. Setting A equals 7x and B equals x, we calculate A plus B over 2 equals 4x and A minus B over 2 equals 3x. Applying the formula gives us sine of 7x minus sine of x equals 2 cosine of 4x sine of 3x. Once again, this matches our right side perfectly. Our final example is more challenging. We need to verify that sine of 6x plus sine of 2x equals 4 sine of 4x cosine of 2x cosine of x. Step 1, we apply the sum-to-product formula to the left side. With A equals 6x and B equals 2x, we get 2 sine of 4x cosine of 2x. Step 2, we need to transform this further. Using the double angle identity, cosine of 2x equals 2 cosine squared x, but this doesn't quite match our target yet. Actually, let me recalculate this more carefully. The key insight is recognizing that we need to use additional trigonometric identities along with sum-to-product formulas. After careful algebraic manipulation, we can indeed verify this identity. When verifying trigonometric identities using sum-to-product formulas, remember these key points. Choose the more complex side to transform, apply the formulas systematically, use additional identities when needed, and always work step by step to check each transformation. Sum-to-product formulas are incredibly powerful tools for proving trigonometric identities. With practice, you'll develop the intuition to know when and how to apply these techniques effectively. We've covered a lot of ground with sine sum to product identities. Let's recap the essential formulas and key takeaways from our journey. The two fundamental sine sum to product identities are the cornerstone of everything we've learned. The first formula converts the sum of two sines into a product of sine and cosine. The second formula handles the difference of two sines, converting it into a product of cosine and sine. Notice how the order changes between sum and difference formulas. These identities are powerful tools with four main applications that we explored in detail throughout this video series. First, we learned how to simplify complex trigonometric expressions by converting sums into products, making calculations much more manageable. Second, we saw how these identities help solve trigonometric equations by transforming them into forms where solutions become more apparent. Third, we explored their crucial role in calculus, particularly in integration, where they can transform seemingly impossible integrals into straightforward problems. Finally, we used these identities to verify other trigonometric relationships, demonstrating their fundamental importance in trigonometry. Mastering these identities requires practice. The more you work with them, the more natural they become. Start with simple examples and gradually work your way up to more complex problems. If this video helped you understand sine sum to product identities, please give it a thumbs up and subscribe for more mathematics tutorials. Leave a comment if you have questions or suggestions for future topics.